Okay, it's 7:30 and we're going to get started. Welcome to the February meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president. And before we get started, we'd like to find out, is there anybody here who this is your first time coming to one of our meetings? Just hold your hand up, tell us your name and what your interest is in astronomy. You guys.
I'm Chris.
Oh, guy, talk in the microphone. Bring
Hi.
the microphone to you.
My name's Chris. This is my wife, Jamie. I somehow convinced her to let me buy a very expensive telescope, and she found this place for us to come and make some friends.
Okay, you came to the right place. Woohoo. All right, who else? First time here. Right, way over there, B. Wait for B to get there with the microphone.
Yep.
We got to run her back and forth again.
Hi, my name is Mike. First time here in person. I've been following the email list for about 6 to 9 months, somewhere in there now. Interests include stargazing, astrobiology, the Artemis missions, and the future of space exploration for the next 10 years.
Excellent. What was your name again? Mike. Mike. Okay. All righty. Who else? First time here.
Don't be shy.
Oh, way over here. I like the way you guys are doing, though. Keep running her back and forth across the room. See? So
I'm counting
back and
my
forth, back and forth.
steps.
Yeah. It's good.
Thomas, first time here. Been watching some of the streams online for a little bit. Yeah, when the weather's nice, I like to break out the telescope and, just.
Great. So you've been watching our YouTube online, huh? You have my sympathies. Oh, one down here. Oh, this is not the first time here.
For those of you that are just coming in tonight for the first time, if you'd like, you can sign up and get on our email distribution, and then you'll get the email monthly reminders for the meeting. So I encourage you to do that.
There's a clipboard out here on the table with a pen and a piece of paper for you to sign up. All right, so who else? First time here? Nobody else. Very good. All righty. Hank. Ready? What's going on here? Not good. It won't advance. Got any ideas? The slides won't advance. Arrow key, enter key, nothing. Escape key, that's going to pop it out, right?
Then you can restart it.
Don't know what he did, but okay, very good. So here's our agenda for this evening. And if you're one of our online listeners, you can submit a question or comment at our email address at the bottom, jscaslive@gmail.com, or you can enter one in as a YouTube comment if you have an account that will allow you to do that. And Trevor Quinn will be getting those questions and comments together and asking our presenters tonight. Okay, the green button blues. Okay, the green button is next to the door out there. When you want to leave, sometimes the door is locked, sometimes it isn't. Like right now it's not locked, but most of the time it is. So when you want to leave, you got to push the green button to the right side of the door. It'll unclick, and then you can open the door and go out. The door shouldn't be open for more than 20 seconds or the alarm will go off. So that's how you get out when you need to leave the building. Okay, a reminder to our presenters. These microphones are wired out of phase, so we got them set like this so that this will actually be picked up by the stream. And you can use this mic or you can use one of these handheld mics if you want. Please use the mouse pointer here. See my mouse pointer? Don't use a green laser pointer because the people online can't see it. B will be running around with the microphone as you've seen. So when someone wants to ask a question, she'll take the microphone and pick up the people who want to ask questions in the auditorium so they can be heard by the streaming audience. Okay. So here's our main speaker tonight, an introduction to Mars's wild yet familiar weather with Dr. Hart Gillespie. Before Hart comes up here, let me tell you a little bit about him. Stay in your seat there. He's ready to go. Okay, Dr. Hartzell Gillespie graduated from the Pennsylvania State University in 2021 with a doctorate in meteorology and atmospheric science. At Penn State, Dr. Gillespie studied a variety of aspects of modern Martian weather, including its traveling weather systems, the 2018 global dust storm, and the northern polar water transport. Prior to Dr. Gillespie's graduate work, he studied at Randolph College, where he was an active member at the Blue Ridge Astronomy Club and observed asteroid occultations. Dr. Gillespie is now a postdoc at the Lunar and Planetary Institute, where we are right now, where he connects atmospheric observations from the Perseverance rover to atmospheric observations made elsewhere on and above Mars. So join me in welcoming Dr. Hart Gillespie.
Thank you, Doug. And let's see if I can work this. Fabulous. Okay, so Doug did all the hard work for me. So that means that I don't need to introduce much about myself, aside from to say that I am originally from Western Virginia, from a tiny, tiny town, so small that there are maybe about 10 times as many people in that town as there are in this room. Yes.
There it is. Okay, Hart, what is that sign behind you? It says Doc Detour. Tell us about that.
That is a trail not too far from Penn State, on the south side of town, not too far from a little town called Pine Grove Mills. I was maybe a few months prior to, well, I guess with the colors there, that'd probably be the year before I graduated. And I happened upon this trail called Doc Detour, and I thought, well, I have to take a picture of this, and I have to hike this because I'm about to get my doctorate. To begin with, I'd like to tell you very briefly about how weather works in general. And to help me do that, I have this little diagram of Earth stripped of all the non-essential features in the bottom right, down here. Weather is the movement and change in the atmosphere over short time scales, primarily a week or less. So the changes on a day-to-day basis, the passage of storms that happens maybe every week, those tend to be the purview of weather. Now, in the case of Mars, a lot of us are also climatologists, so we also study variations on the seasonal and yearly time scale, and I'll be telling you a little bit about those variations as well. The weather itself is caused by differences in temperature over the globe, which are themselves caused by differences in the amount of solar radiation that impinges on the globe in different locations. So if you look carefully at this very crude model of the Earth, bottom right, I have these yellow arrows representing sunlight hitting the Earth. The sun's off to the right side of the screen. And you'll notice that these arrows are closer together, closer to the equator, because they're hitting the equator perpendicularly, whereas they're hitting tangent to the North Pole in this case. So there's more sunlight per square foot, per square meter at the equator than there is at the pole. And this difference, along with the rotation of the Earth and the continents, which I don't have here, cause differences in temperature over the surface of the Earth, which cause differences in temperature of the air, which cause movements of the air, which is what weather is. Put simply, The warmer air, brighter locations, expands, becomes less dense, floats in the colder air up into the atmosphere, and cold air rushes in to take its place. Down here in the blue arrows around the southern half of this mock Earth that I have represents the rough movement of air particles as they travel around the Earth. They will rise in the equatorial regions, travel in the upper atmosphere toward the pole, sink near the pole, and come back toward the equator along the surface. And we call this the global circulation. More on this in a Martian context later. I'd now like to compare Earth and Mars, just to get us familiar with how Mars is different from Earth and how it's similar to Earth in a lot of ways. Of course, Mars is the 4th planet from our sun, and Earth is the 3rd planet from our sun. So Mars is about 50% more distant from the sun than Earth is. That means Mars gets about half the sunlight that Earth does. Mars' orbit is more eccentric than Earth's. It's eccentric enough that you can notice the differences in the seasons. That is to say, southern summer and northern summer are different strengths because the difference in the distance to the sun is noticeable, whereas in the case of the Earth, there's not much difference in the distance, and so that doesn't matter much for the seasons. The axial tilt is what governs the seasons primarily on Earth and also on Mars. They're about the same for Earth and Mars, interestingly enough. That's total coincidence. Mars's axial tilt goes all over the place through geologic time. The length of the day on Mars is about 40 minutes longer than on Earth. Such a small difference that humans could adapt to it if they ever did live on Mars. Mars is a smaller planet than Earth, maybe about half the size, as you can see in the pictures here. And while it is the case that Mars is a smaller planet and so it has less surface gravity, as it happens, a lot of the differences between Earth and Mars cancel out for some of the atmospheric phenomena that we're most interested in. So for instance, something called the scale height, the characteristic depth of atmospheric motion, is about the same for Earth and Mars. And another quantity called the Rossby radius of deformation, which governs the size of storms, is also about the same for Mars, despite the differences between the planets. One particularly humongous notable difference for the two planets is the surface pressure, which on Mars is about 1/100th of what it is on Earth. The surface pressure on Mars is so low that it corresponds to about 22 miles up in the Earth's atmosphere, about 4 Mount Everest or so. The temperature, of course, befitting for a planet further from the sun than the Earth, is lower on Mars than it is on Earth. The hottest it can become on Mars, if you're, say, under the sun on a summer day, it can be perhaps 70 or 80 Fahrenheit. It can be somewhat comfortable for us Earthlings. But at the coldest on Mars, in these polar cap regions, the temperatures can be some 70 degrees Fahrenheit below the lowest temperatures ever recorded on the surface of the Earth, which were recorded in Antarctica, minus 130 or so. Yes.
Can you hit that hide right there?
Can do. Excellent. And just to say, feel free to interrupt at any time with questions. I appreciate having questions during my talks so that I can get some feedback from the audience and so that you can understand my presentations better. So don't hesitate to ask questions. And of course, another major difference.
What is it? axial tilt of the Earth 2393. It's 2333, not 2393.
Oh, my apologies.
Yeah.
I still don't have a problem with you all asking questions. It's good to get these corrections sometime. Better sooner than later. The main atmospheric constituent of Mars is carbon dioxide. There's actually a comparable concentration of there's a comparable pressure of carbon dioxide in the Martian atmosphere to Earth's atmosphere. It's just that Earth's atmosphere has a whole bunch of other stuff in it, like oxygen, very convenient for us. This carbon dioxide in the Martian atmosphere actually freezes out onto the surface at some times during the Martian year, at least in part. And that's what this is down here at the bottom of Mars. That's the southern polar ice cap made of CO2. Let's see what features of Mars we can spot just by looking at a picture of Mars. Take a close look at this picture and see what you can see on this picture that looks different from a featureless orange disk. There's all kinds of things in this picture that look different from a featureless orange disk, which you might see if Mars were in a global dust storm state. Now that you've had a while to take a look, let's see what you spotted. These are what I spotted. Uncratered terrain in the northern hemisphere, meaning it's newer than the heavily cratered old terrain of the southern hemisphere. You can see the southern polar ice cap that I mentioned was made of CO2. And you can see in the north some ice clouds, probably water ice clouds, maybe CO2 ice clouds this far north, it's possible. And you can see water ice clouds and or frost on both limbs of Mars. If you look carefully where this arrow is pointing, you can see a gap underneath the clouds. You can see that the clouds are well above the surface of Mars. So you can get quite a bit of knowledge of Mars weather just by looking at images directly like this. But you can get a lot more information about the weather of Mars by using weather stations. And I show you some of the locations of these weather stations alongside the topography of Mars, which is a lot more varied than the topography of Earth. You have the low elevation northern plains contrasting with the southern highlands, heavily cratered. The difference between the two hemispheres is order 5 kilometers, 3 miles. And this difference has quite a few implications in Mars meteorology. For instance, it's not immediately clear that the differences between the seasons are just caused by the eccentricity of the Martian orbit. The differences in the altitudes of the two hemispheres also impacts the differences between those seasons. Where is Olympus Mons? Olympus Mons is right here, set off from the Tharsis Plateau. Olympus Mons is, of course, the tallest mountain in our solar system, and it just so happens, or maybe doesn't just so happen, to be pretty much opposite the lowest location on the surface of Mars, the Hellas Basin, massive impact crater. There is some thought that the Hellas impact basin caused Olympus Mons and the Tharsis Plateau to form. We don't know. Of course, the conditions around the Tharsis Mountains are quite different from the rest of Mars. For instance, you can see clouds streaming off the leeward side of these mountains. They're so tall that they force air up the windward side of the mountains, and that air, by virtue of rising so much, cools, and the water vapor in the Martian atmosphere, scarce as it is, will freeze into water ice and become. Let's take a look specifically at the Mars surface missions that have returned meteorological data. We've actually got quite a few more than you might think, ranging all the way from the Viking landers back in the 70s to Mars 2020, the Perseverance rover, which I work on here at the LPI, and which arrived in 2021. You'll notice, though, all of our landing sites are in the northern lowlands or immediately adjacent to the northern lowlands. This is because it's easier to land there, and we don't want to lose our very expensive rovers that we send all the way to Mars to a bad landing site. And so this bias in the surface lander data toward the northern highlands, as well as the relative lack of lander sites. Sure, it's nice to have a dozen or so lander sites, but that's not going to tell you what the weather is on an entire planet. So to help us, we primarily use satellite information to learn about the weather of Mars. I want to make note that we actually didn't know that Mars had a low pressure CO2 atmosphere prior to the arrival of Mariner 4 in 1965. There were still some scientists at that time who thought Mars may even have had life, but certainly the possibility that the channels so rumored in the past were water features. In more modern times, we have Mars Global Surveyor, Mars Reconnaissance Orbiter, and the HOPE probe from the United Arab Emirates that each have one instrument on them that provides information about the Martian atmosphere. And to help show you how they do this, I have prepared this diagram. This shows the measuring strategies of each of the three instruments aboard these satellites. The oldest is the Thermal Emission Spectrometer, or TESS, which is a polar orbiter. That is to say, it orbits close to the planet and orbits from pole to pole, gets information at about 2 a.m. and p.m. local time, pretty much everywhere on Mars. It looks straight down at the planet of Mars. As a result of looking straight down at the planet, you get plenty of information throughout the depth of the lower atmosphere. You don't have to worry about dust or water ice clouds blocking your sight most of the time. However, because you're looking straight down through the atmosphere, you don't get a lot of information about the various vertical levels in the atmosphere. You don't get a lot of vertical resolution. You get a lot more vertical resolution when you look at the data from the Mars Climate Sounder, which looks out onto the edge of Mars through a long path through the atmosphere. And as a result of that, you can get more vertical resolution out of MCS data. However, because you're looking through a long portion of the atmosphere, your observations can be blocked by thick clouds like the ones that are on the top of this image. The third instrument, the one that's most recent, is called EMIRS, and it, uniquely for Mars weather measurements, provides information about the entire disk of Mars. Nearly half of the Martian surface is visible to the EMIRS instrument at any time. And as a result, it gives you the best picture of what's going on at the global scale. However, the trouble with EMIRS is that its associated satellite travels quite slowly around Mars. So you don't know what's going on at a particular location for a day or more. And the weather on Mars happens to change at scales on the order of a day. The HOPE orbiter is not in an areocentric orbit. It's over a specific point on Mars. It drifts over the planet in an orbit that defies quick description, I would say. I believe it takes about 2 days for EMIRS to see the entirety of the Martian disk that it can see. Can't see quite the entirety of Mars.
Art, excuse me, can you repeat the question that was asked because it didn't get picked up?
Yes, so the question was about the orbit of EMIRS. The question was, is the HOPE orbiter in an aerostationary orbit? And the answer is no, it's not. It drifts around the planet of Mars, and it takes a bit more than 2 days for it to get all the way around. I primarily use computer simulations as a tool to understand Martian weather. To do that, I use basic physics, the conservation of a momentum, mass, and energy, and I combine the equations that you get from those, which are called the primitive equations in meteorology, with satellite observations, the light observations that I was describing to you earlier, using a process called data assimilation to create what's called a reanalysis data set. That resulting reanalysis data set provides information from the satellites, which tie us to the weather of the real Mars, and information from the basic equations of physics, which tell us what's going on across the entire planet, not just the parts we can see, but also the parts we can't with our instruments. Using both of them together, we get a picture of what's going on the real Mars everywhere, and for all the quantities that we might be interested in. For the remainder of the talk, I want to explain Martian weather and climate by using 3 cycles. The CO2 cycle, which of course CO2 being the dominant component of the Mars atmosphere, I think is the most important to understand. The Mars water cycle and the Mars dust cycle, which is the most peculiar of the 3. For the Mars CO2 cycle, this is primarily an exploration of the climate of Mars and of how the CO2 in the Martian atmosphere is transferred from one pole to the other and back over the course of the year. As I mentioned before, solar radiation controls weather, and the air ultimately moves because of differences in the amount of light that different places across the planet get. For Mars, here's how much light the Martian surface gets on the average in watts per meter square. You'll notice, for instance, at the spring equinox, as you would expect, the equator is where is the location on the planet that gets the most light. What you might not be so aware of is that on Mars, and indeed too on Earth, near the summer and winter solstices, the respective poles are where the most light is received. Mars is a desert planet. It doesn't have the giant oceans that Earth does that act as a heat sink. And so for Mars, the location where air rises over the course of the year changes by quite a lot more than on Earth. On Earth, that location where air primarily rises is confined to the tropics, a region called the intertropical convergence zone. On Mars, it moves not only through the tropics, but also through the mid-latitudes, well poleward of where Texas is on Earth. You can see this transfer of carbon dioxide from pole to pole when you look at pressure data. Originally, the pressure data from the Viking landers showed us the CO2 cycle, but we've also had pressure records from pretty much every instrument on Mars that bothered to have a weather package. They pretty much all included pressure data. You'll notice if you take a careful look at this graph of the pressure of the surface of Mars, first off, that you have higher pressures near the solstices and lower pressures near the equinoxes. Specifically, they're shifted a bit before the solstices and the equinoxes. And what's going on here is that in the, let's pick a start time. I will start us at 90 degrees LS. That is to say, the southern summer. The southern summer is where we'll start. Don't mind me, just being backwards. The southern summer. Okay, I'm not out of my mind. So at this time, the southern pole is illuminated the most on the planet of Mars. That is to say, the CO2 has vacated the southern pole to the extent that it will, and is migrating toward the northern pole. And it'll migrate toward the northern pole until the northern pole is almost illuminated. Because the northern pole, of course, at this time during the southern summer solstice is in polar night, and the CO2 can condense directly on the surface or snow out of the atmosphere. Once the northern pole becomes bright, that CO2 then sublimates from that pole and makes its way back to the south. And the process repeats in the other direction once you reach the northern summer solstice. We can show how this is happening through plots like these. In the top left, we have what's called the circulation of the atmosphere, the meridional circulation. And the way this plot works is it's showing you which direction the air is moving, but along the contours rather than in some other direction. The positive values indicate that the circulation is clockwise. So for instance, at this time, just after the fall equinox, you have this circulation cell dominant in the northern hemisphere. But you also have a little bit of circulation in the southern hemisphere. You can see the winds on Mars. The U wind is the zonal wind. That's the east-west wind. And positive values of this means that the wind is blowing from the west to the east, as the winds primarily do in Earth's mid-latitudes. You'll notice that the wind speeds on Mars at this time can reach as high as 100 meters per second, some 200-ish miles per hour. Is not uncharacteristic of the Martian jet in the equinoctial season. This isn't so unusual. Earth has values about like that. And in general, this whole circulation pattern looks quite a bit like Earth's does. You have the polar jet. Now Earth, as it happens, has two jets. It has a polar jet and a subtropical jet. And you can maybe convince yourself or not that there's a subtropical jet right here. I don't know. You can tell me what you think. Between the V and W, you can see the circulation in more detail. You can see that the air is rising near the equator, traveling poleward in both hemispheres. As you see from the V wind, the meridional wind, the north-south wind, where positive values mean north. The air is descending in the mid-latitudes, somewhere on the order of 50 north or so. And then it returns back to the equator. We call this main circulation the Hadley circulation. for both Earth and Mars. We call this, whether I've heard some Earth dynamicists disagree in calling this the Hadley circulation. But as far as I'm concerned, it's the Hadley circulation. Works the same way, yes.
So you say Hadley. When I think Hadley, I think it's like 10 to 20 degrees of latitude on Earth for the Hadley cells, and they go around.
I would say
Up and
closer
down.
to 30, but yes.
But you're saying here on Mars that your Hadley cell is the entire planet.
The Hadley cell is about 60 degrees
Oh,
at this
okay.
time. So there's a little bit of room outside the Hadley cell at both poles at this time of year. Now remember, Mars is about half the size of Earth. So these Hadley cells in the solstitial season, or rather, sorry, in the equinoctial season, are about the same size as the ones on Earth. But it gets stranger.
So what does the barometric pressure have to do with the Hadley cells? Because it makes a gigantic difference here on Earth.
I'm not sure that the difference in the surface pressure makes all that much difference in the way the Hadley cell operates. The fundamental physics is, of course, the same. You have the difference in the solar heating across the planet, averaged east-west along lines of latitude, and those differences are what cause the Hadley cell to exist. One thing you'll notice about this that's pretty peculiar if you compared it to the Earth's Hadley cell is the height of the circulation. The Martian Hadley cell circulation extends upward from the surface to perhaps 1 Pascal. And to give you an idea, each tick mark in the vertical here is somewhere on the order of 10 to 15 kilometers, 6 to 10 miles or so. The Earth's Hadley cell is perhaps only 10 miles tall. So the Martian one and the Martian circulation in general is quite a bit deeper than Earth's. And really, we don't have a full understanding of why that is. We have some understanding of why that is. In part, Mars doesn't have any ozone to suppress the troposphere's height. But I believe a full understanding is still somewhat elusive. Now that's what happens in the equinoctial season, but in the solstitial season, things become even weirder. Put simply, the Hadley circulation at this time does form a much closer approximation to covering the entire planet. The air will rise somewhere in this case, this is northern winter, southern summer. So the air will rise somewhere in the southern mid-latitude, somewhere order 30, 40 degrees south. It will travel up over there and then across the upper part of the Martian atmosphere down toward the northern pole. On the left here, just to give you an idea of what's going on in these figures, on the left here is a product that I helped create called eMars. This is one of those reanalysis data sets I was telling you about that incorporates information about the real Mars atmosphere and a weather model. And on the right is information from a free run, we call it. That is to say, the same model, but without the observations from the satellites, just tuned to work somewhat like the real Martian atmosphere as best we can do otherwise. And you'll see there are some differences in the way the Hadley circulation works, but in both cases, you have descent in the northern polar regions. The color here is showing temperature in kelvins. The highest temperature on this scale is still around 0 Fahrenheit or so. And the lowest temperatures on this scale are something like minus 170 or so. So it can get quite cold on Mars. And you can see this sharp gradient between the warmer tropics, but still absolutely frigid for us, and the colder polar regions, where the CO2 ice would be deposited onto the surface at this time. As a summary for the CO2 cycle, around the solstices, you have CO2 sublimating off the summer pole. It gets off the summer pole near the surface, then travels up in the atmosphere. Once it reaches the mid-latitudes, doesn't get too far, then it proceeds across the top of the atmosphere through the cross-equatorial Hadley circulation and sinks at the winter pole, either being deposited onto the surface, being snowed out onto the surface in CO2 clouds, and not all of it gets snowed out. Some of it goes back in a return flow along the surface. And when the seasons change, the cycle reverses with a brief period of relative Earth-like circulation in the middle. I want to touch on the Martian water cycle because there is water on Mars. It's just not liquid. There's water vapor and there's water ice, and they matter for Mars. You can see the Martian clouds as you did in the early pictures in my presentation, but there's no water. We've been working on understanding these clouds for quite some time, in particular, the radiative effects of these clouds, that is to say, the effect of light being bounced off the clouds and absorbed by the clouds and what have you. And we still don't have a full understanding of Martian clouds, in particular their radiative importance. Basically, all I can say in that regard is that I've done some looking at the Martian clouds, and that most scientists can agree at this point that they are radiatively important. If you don't include them in your models, you will have errors. Mars is a dry planet. So I didn't point out on this figure that I showed you from earlier that there's also water information embedded in this figure. In the black is the meridional stream function, again showing roughly the direction of movement of air on Mars clockwise around the positive values. But also in the red, which you can very faintly see here, the red contours, those show you the amount of water vapor in the air, and in the white, you see the amount of water ice in the air, both in milligrams of water per kilogram of air. And to give you an idea, here in Houston, often the amount of water in the air is on the order of 10 grams per kilogram, whereas on Mars, you've got 10 to 100 milligrams of water per kilogram of air. Mars is a very dry planet. What I find most interesting about the Martian atmosphere is the Martian dust cycle, which we don't really have any equivalent to on Earth. The closest equivalent you get to the Martian dust cycle on Earth, in my opinion, is Earth's clouds. While Martian dust can't evaporate or condense or freeze like water on Earth can in its clouds, the importance of dust in the Martian atmosphere is as paramount as the importance of water in our own atmosphere. The Martian dust, in many ways, in the Martian atmosphere can act as thick clouds do in the Earth's atmosphere. And there's a lot we don't understand about the Martian dust cycle, as hopefully will become clear as I go through some of the points of the dust cycle. Dust is transported at all scales on Mars. Shown here is a particularly famous dust devil on Mars. Now, we have dust devils on Earth too, but the dust devils on Earth are quite a bit smaller than the Martian dust devils. The Martian dust devils can be perhaps 1 kilometer tall, nearly half a mile, and Earth dust devils are often 1/10 of that, or even less. We don't know how dust gets into the free atmosphere of Mars well off the surface. It could be that dust devils are the most important part of getting dust off the surface of Mars. It could be that little grains of or that little grains of dust interacting with bigger grains near the surface of Mars can cause those bigger grains to bounce and dislodge smaller grains of dust, putting them into the atmosphere in a process called saltation. It could be that there are these things called rocket dust storms, these bodies of dust in the Martian atmosphere, perhaps on the scale of kilometers or so, that lift themselves during the day with the help of solar radiation. We don't know. There's a lot we don't know about the dust cycle, and perhaps first and foremost about what we don't know about the dust cycle is how the dust gets off the planet in the first place. But once it does, we can start to tell you quite a bit about what's happening with that dust. At the regional scale, dust is transported by the large-scale winds in the Martian atmosphere. And it also sediments a bit because it has some weight. These are some dust storms from 2002 in the spring in the Northern Hemisphere. Here you can see the northern winter polar ice cap near its maximum extent. And just off the edge of this northern polar ice cap, you can see these dust clouds. Some of them look like they've got a bit of rotation going on. Others of them look like maybe more straight line winds. This one over here, that's anybody's guess as far as I'm concerned. This picture of Texas is to scale for Mars. So these dust storms are quite large. It should perhaps be no surprise that these dust storms are this size because Texas is roughly the size of storms on Mars and Earth. The atmospheric physics dictate that storms are roughly this size. This is the Rossby radius of deformation that I was referring to earlier on, roughly about the size of Texas. The reanalysis product that I helped create called eMars shows us, in addition to prior data from the surface of Mars, not least the Viking lander that was put there in the 70s, showed us that there were these traveling waves, these transient eddies, traveling weather systems that cross the planet of Mars, generally near the winter polar ice cap, where there's a large difference in temperature between that cold CO2 ice in the polar region and the warmer air in the mid-latitudes and tropics. So along this ice cap edge, you have these storms that propagate from west to east, just like they do on Earth. We have these same storms on Earth too. And they propagate around the planet with a period of about once a week. That is to say, it takes about 1 week for any one of these individual storms to get all the way around the planet Mars. Shown here are changes in temperature induced by these storms in the red and blue contours. The units here are kelvins. So you can see temperature changes induced by these storms, perhaps as large as here I see almost 40 Fahrenheit, 20 Kelvin, 20 Celsius. And in the solid and dotted contours, you see changes in pressure in pascals. These are about 1/10 mean atmospheric pressure of Mars. To give you an idea of just how big that difference is, the most intense hurricanes on Earth have pressure differences from the mean of Earth of about 1/10. So these are quite significant pressure perturbations. You have regional dust storms caused in part by these traveling weather systems 1 to 3 times every Martian year. They're quite reliable. What changes about these storms from year to year is primarily their size and their intensity, the amount of dust that they kick up into the atmosphere. But you can pretty much count on one of the storms to be quite strong, one of the storms possibly to be strong or weak, and one of them may or may not exist. There are roughly 3 in a Martian year. In these storms, it's often hard to see long distances, so solar power is a concern on Mars during these regional dust storms, but more so during the most radical feature of the Martian atmosphere, the global dust storms, where the entire surface of the planet of Mars can be obscured for months on end. During a global dust storm, opacities can be so high from the dust that more than 99% of the light from the sun will interact with the dust in some way, whether it be absorbed by the dust directly or be reflected by the dust, perhaps to be absorbed by some other dust particle. On the surface of Mars, at these times, it becomes quite dark for a long time. And so it's dust storms like this one that present the biggest challenges for solar power on the surface of Mars, as was shown by our long-running Opportunity rover failing during the 2018 global dust storm after some 10 plus years of service. I showed in my only first author paper, actually, that the 2018 global dust storm had dust entrained into it by the global Hadley circulation. The storm in that particular case started in the northern hemisphere, perhaps from some little perturbation from one of the storms that was about, at that time, one of the traveling weather systems that you expect on Mars and on Earth. That dust was blown toward the equator, lifted by the Hadley circulation, traveled back out to the zonal jet, where it was easily spread around the planet by the strong winds in the zonal jet. We don't know much about the formation and growth of global dust storms. This is what I was able to figure out from the 2018 storm. I don't know whether this applies to other storms. In fact, I can tell you for sure that the early details are different in other storms. We know that other global dust storms started in different places. And so they had to become global in some other way. We also don't know why global dust storms occur in some years and not others. Global dust storms on Mars happen every 3 to 5 or so Mars years. And we don't know why they happen at particular times and not others. The most likely hypothesis, yes?
Is there any link between perihelion, is that the right term for it, and the presence of the dust storms, global dust storms?
There is. That's a very important point. So most global dust storms happen around perihelion, as it happens, and as you might expect, because at perihelion, you've got the warmest temperatures on Mars. This is where that difference between the northern summer and the southern summer comes in. Perihelion happens to occur near the southern summer solstice. So around the southern summer solstice is the prime time for global dust storms to occur. However, we've also seen that global dust storms occur near the autumnal equinox. Now, perihelion does happen to be between the southern summer solstice and the autumnal equinox, so maybe you could say that perihelion is having some impact on the storms happening at that time and not the vernal equinox. But we don't really know why those storms are happening at the autumnal equinox. You would think that the dust would be lifted primarily around the solstice, when the Hadley circulation is strongest, when the insolation is strongest, the solar radiation onto the surface is strongest, when the differences in temperature are greatest, which drive the winds. But that doesn't always happen, and we don't know why. Summarize these knowledge gaps. One of my collaborators, Claire Newman, wrote a paper including the 4 knowledge gaps that are important in dust transport and in understanding the Martian dust cycle. And from these 4 questions, you might understand that we really don't know much about the most important cycle on Mars for day-to-day weather. We've got a lot to learn about the atmosphere of Mars, and that's part of my work here at LPI, using observations from the Perseverance rover, learning more about what's happening on the surface of Mars, collecting more data, observing more global dust storms. Hopefully we'll get one of those at some point soon. And understanding more about the Martian dust cycle and about the other processes that happen in the atmosphere of Mars. Thank you for your time.
Okay, quick question. Okay, are your computer modeling getting updated based on the actual observations? Because I know you said you're using the computer modeling to predict, and you're collecting the data of actual, Martian weather.
Yes.
How quickly can you update your computer modeling?
So the way this works is that you get the observations well after they've occurred. So there's a lot of implications to that, and I'll go into a few of them as an answer to your question. But we get the observations from Mars, we retrieve those observations and learn from them, because all the instrument is seeing is the amount of light that's coming into its sensors. It's not seeing temperature directly. So you have to do those conversions, and you can do those in varying levels of detail to get improved estimates of, say, the temperature. Then we ingest those into the model well after the fact. I think for EMARS, we are about 6 years behind or so at the moment, just to give you some idea. And that's not at all unusual. There are 2 long-term active reanalysis projects for Mars, and EMARS is one of them. So it takes a while. In principle, we could get the data in immediately, or perhaps only a day afterwards, if we had some way to transfer the retrievals as soon as they were made into our model and run the model automatically. And if you do that in a quick enough time, you can run the model past the current date. And then what you have is Mars weather prediction. Hopefully, I'll get to do that sometime soon. Hopefully that answers your question.
Art, what is the orbital or period of precession of the poles? On Earth, it's 26,000 years. And is there a Milankovitch cycle in which the orbit is distorted by the gravity from Jupiter?
So there are Milankovitch cycles on Mars. I don't know what the period of precession is for the Martian pole, but it has one, of course. And it's the same order of magnitude of time. It doesn't go a whole lot faster than Earth's pole, and it doesn't go a whole lot slower than Earth's pole either. As for the distortions of the orbit with Jupiter, I recall something about that, but I don't recall the period off the top of my head. I do know that there is an 11 to 12 year or so period that is important in one of the hypotheses about when the global dust storms happen. And I don't remember exactly, but that might have to do in some way with Jupiter. It's not typical that that other planets affect the weather on a planet. For instance, as far as we can tell, that doesn't happen for Earth, aside from as far as we can tell, that doesn't happen for Earth on a human time scale. Not even the moon is included in weather models to give you an idea. You don't need it. But for Mars, maybe it matters. I'm not sure.
Yeah, first, I'll come to you.
Is there any evidence of lightning in these storms, or is any?
Yes,
Like-
there is lightning on Mars.
No, there's.
We have detected, I believe it's Whistler waves, I think they're called. But I know that we've detected lightning on Mars.
Why is the data so delayed? Why is there a 6-year gap?
That's because it's me who has to do all of this work, and it takes time. Now, to be fair, I don't do all of it. My previous advisor has had other students and does have other students, but it takes time for us being a small group to do the work. And of course, I think another big factor is the 2018 global dust storm. That made our model go a little haywire. So we need to do some modifications to make sure that our reanalysis is stable through that. That's the reason. Small group.
Does the water vapor, does that help to get some of the dust in the air? And is it like water ice brings dust with it and then sublimates or something into the water vapor and then releases the dust?
In some cases, perhaps. So something that does happen is that water ice and also CO2 ice can condense, or sorry, they can be deposited onto dust particles. The dust particles are then called ice nuclei, imaginatively, I know. And so you might imagine that when this ice sublimates, or when it's deposited onto the winter pole, it leaves dust behind. I don't think that's terribly important as a mechanism of moving dust, but I also know that other people beg to differ.
I have like 2 or 3 questions for you, if you don't mind. Maximum wind speed on Mars. I teach astronomy. I'd like to know this to be able to pass it on my class.
350 miles an hour, I think, is a pretty typical maximum zonal mean wind over the course of the year.
But with no pressure associated with it. So what does that really, I mean, we get 350 miles an hour here, we got problems. You don't have enough atmosphere there, so what does that really mean?
Let's see, what would that feel like? So kinetic energy of the winds goes as velocity squared. And of course, the density of the Martian atmosphere is some 100th of Earth's atmosphere. So that would feel like a stiff gale, I guess. You might have to put up a little resistance to walking in it. Mind you, this is something like 50 kilometers above the Martian surface. So you're not walking in it. But if you were up there, of course, there's lower pressure up there too, but if you had such winds at the surface, it'd just be a stiff gale. Up at those pressures, it'd be feel like a light breeze, I suppose.
All right, next question would be, does Mars have an equivalent to a jet stream like we do here on Earth?
Yes. And it's the winds in those jet streams that I just quoted you the wind speed value for.
Is it at the interface of the troposphere like it is here on Earth? Does Mars have a troposphere? Does it have a stratosphere?
Ah, the challenging question.
Oh, I got more for you.
So, most Mars scientists, I think, will say that Mars has a troposphere, a stratosphere, and a thermosphere. And of course, it has an exosphere. They will say it doesn't have a mesosphere. If you ask me, I am a bit wishy-washy. Sometimes I will say that Mars has a troposphere, and then the next layer above the troposphere is the thermosphere. And other times I will say that there is, in fact, a stratosphere. Let's see if I can give you some ideas. Okay. We should go. Sure, we'll go with the wind plots, even though there's no temperature information on there. So this is the troposphere. If you ask me, this is the troposphere. This Hadley circulation is all in the troposphere. The part that you might say is stratosphere is over here inside the polar jets, or when there's only one polar jet inside just that one. This is a little region of stratosphere. Maybe. And the thermosphere is up top. Just at the top of these models.
All right, so I guess I'm really confused about stratosphere. When I think stratosphere, I think of a horizontal layer above the surface of the planet. When you're showing me that, it looks like a vertical latitudinal gradient instead.
Well, remember that, and sorry, I think I mixed those layers up. Of course, the bottom layer is the troposphere. So you would call the polar troposphere this part, and the stratosphere the part above it in the polar regions. But it's important to keep in mind that the scales here in the horizontal and the vertical are heavily, heavily distorted. The vertical scale here, the entire plot covers 100 kilometers, give or take. That's about 100 kilometers there in the vertical. And this horizontal is, let's see, what's that? About 10,000 kilometers. So really, if you want to make this look the shape that it's supposed to be, you got to stretch that horizontal part out 100 times. And so while it looks like it's a vertical slice when I show it to you on this plot, really it's a whole lot more horizontal than that. These plots have tricked me many a time into thinking that something is a lot more vertical than it really is.
So I'm sure you've got adiabatic processes on things like Olympus Mons and the Tharsis Plateau volcanoes. Is there enough of that present to produce something like a fin ladder jet?
Fin ladder jet.
Yeah, that's the thing that drives the southwest monsoon over the Horn of Africa.
I'm not convinced that there is, but I'm also not, and I would lean against it, but I'm not 100% convinced that there's not. If you wanted to see something that's, I don't think Mars has much in the way of monsoon-like winds, because of course the monsoon winds are driven by the difference between the ocean and the continental landmass, and you just don't have anything like that on Mars. There's nothing with such differences in heat capacity.
I was thinking that maybe elevation would drive it between the depressed northern hemisphere and the elevated southern hemisphere. That's why I was curious about that.
Sometimes you do get katabatic winds flowing off the mountains, and off the polar regions, you get those a lot more. They're actually very common in the polar regions. And so that wind can behave sort of like a monsoon. You may also get some associated winds along the edges of the mountains. You can have western boundary currents, they're called, and that can flow in quite strong, concentrated batches. And they actually oftentimes will drive storms, regional dust storms that grow in the northern hemisphere into the southern hemisphere, where they can then expand.
It works. In discussing the dust cycle, you talked about dust being uplifted and deposited elsewhere. That's dust going up and down. Now, against gravity and then being pulled down by gravity. Of course, gravity on the surface of Mars is a lot less than it is here on Earth. Does that does that make the circulation of dust on Mars different from what it might be here in a noticeable way?
It would be different, yes, for sure. As for the extent of the differences, I'll be honest, I don't think we know the entire extent of the differences. So for instance, right here on this slide, I'm showing you a deeper Hadley circulation on Mars. And I don't think we fully understand, for instance, why the Hadley circulation on Mars is so much deeper than it is on Earth. And I think that precludes us, at least in part, from understanding the full details of the differences between the Martian dust cycle and the putative Earth dust cycle.
Thank you, Hart, for that very interesting presentation. And obviously, like I said, there's a lot of interest, so we'll continue this later at Mod Pizza. Next up, Ron, tell us about the DVD library.
I'd like to repeat something that Doug brought. We have a clipboard at the front desk. If you did not get an email about this particular meeting, you can please give us your email address. There's two areas that one is you just want to know when the meeting is. The other one is the conversation that goes back and forth all month long. So, yes, for the first time in 3 years, the library is back. And I've got about 30 more that have been given to me. So if you've made a couple of meetings, please feel free to take out a DVD. There's all tons of subjects. If there's a code, there's a key on the top. IC is the Infinite Cosmos by, which is astronomy magazine. There's NASA, there's the great courses, there's all kinds of stuff. Now, if they're marked black, they're missing. And I haven't certainly most of the red ones are gone now too. So anyway, but I'll be adding a lot more. So if you've made a couple of meetings and you're going to come back and bring it back, please feel free to do so.
Thank you, Ron. Okay, so the meeting, after we get done here, we're going to zip off to Mod Pizza. Here we are, Lunar Planetary Institute, go up Middlebrook, take a left on Clear Lake City Boulevard, across El Dorado, and right in front of the HEB, there's a Mod Pizza. We'll get together there and continue our discussions of astronomy and other topics. And we're going to take a short break, believe it or not. I think this is the first time in many meetings. We're going to take a break. So 10 minutes seems too short, 15 minutes seems too long, 12-minute break, and we'll start up again in 12 minutes. Go out and see the DVD library. Get yourself a DVD from Ron. A lot of fun watching you run back and forth, though.
I think Trevor on this.
We're figuring out how to do it, so you're right.
Because we're running.
Okay, yeah, we'll make sure Trevor's okay with that.
I
Crazy.
can stay on the back and
Talk to Trevor. Oh, where'd he go?
yeah.
Ask him about our idea. See what he says.
You know the way emails work. If I drop one letter.
I get it.
I was catching up on. Did you want to do the rest of it?
No, I'm good. I'm gonna go back.
Okay, go back. Okay, we're going to get started, so the lights are going down. Take your seat so you don't hurt yourself. Okay, we are going to get started. You guys don't believe me, do you? We are really going to get started. Let's see, there's B up there, not paying any attention, and there's Brandon not paying any attention, and I'm gonna have to get the cowbell out if you guys don't sit down and be quiet. Come on. You guys. Next time we'll have a half-hour break. Okay, we're moving on. DIY astronomy, views of, okay, now that's what I'm gonna say, because you guys, you know, if you've been around the astronomy community for any amount of time, you hear these words pronounced all different ways, right? So how do you guys pronounce this one? I'm hearing Auriga. That's not correct. Anybody else? Who's that? Who was that? What'd you say? He's right. According to Night Watch by Terrence Dickinson, if we believe them, I don't know. They say that the correct pronunciation of this is Auriga. Okay, so I've been pronouncing it like the way Jim's been pronouncing it my entire life until this week. I've been calling it Auriga, but now I'm going to call it Auriga because that's apparently the correct one. So who knows? All right, so if you look for this constellation, It's actually up now. It's a nice winter constellation. It's this pentagon-ish shaped little doodad over here. See, Auriga. The brightest star is Capella up here. But when you look at this in a dark sky, you know, with your eyes or with binoculars, you see there's a lot of stuff going on down here in this area. There's a lot of different celestial objects. And that's what we're going to be talking about tonight, this area of Auriga. This is a hydrogen picture of this area that I took with a 50mm camera lens. So this is a fairly wide image. And inside this image, you're going to see a lot of stuff. There's some IC objects, these emission nebula here, IC object, IC 417, 410, 405. Then there's some sharpless 2 objects, and these are hydrogen gas areas. There's NGC, that's actually another emission nebula. And there's some open clusters like M38 and M36. And if any of you guys are visual observers of this area, you'll think, well, wait a minute, where's M37? Because these are the 3 famous clusters in Auriga. And M37 actually is just off the screen down here, so we can't see it. So there's a lot, my point is there's a lot going on in this area. It's kind of interesting. Now, the other thing, this kind of bothers me because when we look at this, supposedly IC 417, this guy over here is about 7,500 light years away. Then IC 410, this one right here, is about 12,400 light years away. IC 405 is about 1,500 light years away. So this bothers me because when I look at this, I thought these guys were all associated with each other because they're in the same exact part of the sky, and there's a bunch of gas and dust and a nebula there. I thought, well, they're all together. But apparently these guys are like way off from each other, which makes me wonder why in the world they're all right in the same field of view, right in the same direction that we're pointing. So you guys can contemplate that. And maybe, you know, do we really believe that? I don't know. But that supposedly these are not associated with each other. And then the 2 open clusters are those far away. Now we're going to look at this area right in here, zoom in on this. So this is a 4mm lens, pretty wide. This next image, this is with a 200mm lens, so it's a little more zoomed in. And here again, we've got IC 417, which you just saw in the previous one, and 410, and then 405 down here. So now these, they're actually, even though they're all emission nebulas, they're actually not composed of the same thing. And even with an amateur telescope like this was taken with, this was actually taken with, even with a camera lens, not even with a telescope, you can see that they're different. And these are done with narrowband filters. So the IC 417, actually, I got a low for sulfur and high for hydrogen and then a low for oxygen. But when you look over here, IC 10, I got a low reading for sulfur, high for hydrogen, but then I got a medium for oxygen. And oxygen is this blue region in here. So blue is assigned to oxygen. And then again on IC 405 down here, I got a low sulfur reading, high hydrogen, but then low oxygen. So even though they're all emission nebula, they all don't have necessarily the same composition. You can actually see that even with amateur equipment. So again, this is a 200mm camera lens now. This next image, this is taken with a 1200mm telescope. And I took this one just more recently. This was taken in December. So IC 417 was this one up here in this picture with a 200mm camera lens, and then this is with a 1200mm refractor telescope. So we can see this a little closer and see what the structure looks like. Now, what I wanted to point out on this one, and this is a whole lot of I don't knows presentation, yes, what you can call this. You look at this, there's this thing down here. Look at this. There is, and I've taken pictures of a lot of nebula, and I have never seen something exactly like that. And I've looked at this before, and I think this is very peculiar. This is like a corkscrewish type area of gas and dust, and there's actually on the opposite side of this thing is something shooting out the top of this. And who said that? Somebody. Okay, that's what I'm wondering. And I did a lot of reading about this, but I can't find anywhere where anyone explains what in the world this thing is on IC 417. So I'd like to say I know what that is, but I think it's pretty cool. And I'm kind of wondering about that. And if any of you know what that is, maybe it is some kind of jet, but it seems very strange that a jet is usually caused like when you have a galaxy or something, there's a jet coming out of the top and bottom. Maybe. It could be. So something's going on there. Okay, so that's IC 417, 1200mm focal length telescope. All right, So more recently, in January, I had a visiting professor that came to stay with me for a week while his family was on a cruise. And he helped me set up our homemade refractor telescope in the backyard. So this is the same telescope that took the previous picture, but the difference is instead of being at 1200 millimeter focal length, by use of a focal reducer, I had this one set for these images I'm going to show you next at 848 millimeters, which also took it down to f6.8 so the exposures aren't as long. So that's our homemade telescope. If you've been around this club for a while, you'll know that I keep bragging about this telescope because it was very cheap and it actually works pretty good, even though it didn't cost very much to make. That's a piece of Hastings irrigation pipe there. And then it's a lens that I bought at the Texas Star Party for 20 bucks. So the whole telescope is very low cost. So the next image I'm going to show you, there are more narrowband images. And these are, the one thing that's different though is all the ones I was showing you previously, I used all beta narrowband filters, hydrogen, sulfur, and oxygen. But these next ones are my first night using a 3 nanometer Antlia filter. And what's significant about this, okay, so as you guys know from living around here, we've been getting more and more street lights, blue LED-ish street lights that are very bright and very awful. And where I live, our Bortle level actually has changed one number since they started putting these street lights in. But the problem is it doesn't really affect so much hydrogen and sulfur, but in oxygen, I've been having a lot of trouble with sky gradients because of the wavelengths of the light of the LED lights are very prevalent within around where the oxygen emission is too. So my previous oxygen filter was 8.5 nanometers, so it's quite a bit wider than 3 nanometers. But with this 3 nanometer filter, I got a lot better sky gradients because it's much more narrow. It doesn't let so much of the sky in, just only the emission lines. Okay, so this is, now I'm going to back up here. IC 410 is this one over here. Okay, and again, that's with a 200 millimeter camera lens. Now here's IC 410, but with that 848 millimeter basically telescope. So this nebula, as some of you may know, is called the Tadpole Nebula because these two guys down here look like tadpoles. And so it's called Tadpole Nebula. This is hydrogen only. That's why it's black and white. Tadpole Nebula, a lot of good detail in this. So again, this is our homemade refractor. Can't complain for a telescope that costs less than $200. And then this is the same image, but this is a starless image. And with image processing, it's actually fairly easy to take the stars out so you can emphasize the nebula and not be distracted by the stars. So that's with all the stars in it. And this is with the stars taken away, so you can actually just see the nebula without the stars. Hydrogen only. And then this is a color version of the same image. This is hydrogen, sulfur, and oxygen again. Same nebula. And tadpoles down here, you can really see these star-forming regions down here, the tadpoles in this one. And these are supposedly ionized by these stars in this region here. That's why they're brighter on that side. So a couple things. I mean, this is something you can, I live about a mile north of here. You can do this in your backyard. I can tell you it's easy. I'm going to tell you it takes a lot of years of work to be able to figure out how to do this. But even with light polluted skies, you can get images like this, in this round. Okay, my last image here, this is the starless version of that same color image. IC 410, the Tadpole Nebula, starless. That's what I got. Okay. And if you want to see other of my work, you can see them on my webpage, www.holland-observatory.net. Next up, we have Trevor with another DIY astronomy quick image processing using Cyril.
All right, this came about because Doug presented last month on Cyril, and I decided, well, let's try it out. So this is the main interface of Cyril. Basically, you take all your frames, in your calibration frames, which I have in the folders there on the right side. You'll go up to this area here and set your home directory to be where those files are. Once you have those folders with all your files in it, you'll come over to this scripts area and begin from there. And we'll go ahead and advance. So you set the working directory, like I said before. You go to the scripts, and in my case, I chose the one-shot color script that's automatically in there. And I executed that script, and you can see the script running there on the side, and that's doing all your rejection stacking. Which once that gets done, it generates a file called results.fit. And then you'll load that back into the program to continue the processing. And the first bit of processing I do, before I get into that, down here, let's see, where is it? Down here where this cursor is, this is a little auto stretch region. You can tell it to auto stretch. Now this does not, at this point, this auto stretch does not affect the linear data. This is just a view version auto stretch, so you can see what you're working with. And the first option I'm doing is I'm going to go ahead and do a crop because I'm going to see some gradient down there at the bottom, you know, some light bleed, and that's from my camera sensor because this was with my Nikon. So it has a lot of bleed from the, what is that again, Doug? The amp globe. Yeah, thank you. Now, so my initial processing of this image ended up looking somewhat like what you see in that auto stretched. You know, there's not a whole lot there. You got the Orion Nebula, then you got the Horsehead and the Flame, but there's just not much else there. And that's what it looked like when I first processed it way back in 2020, because this is from Eldorado Star Party data. So we'll go ahead and move forward. The first bit of information that you do is you do a background extraction, and this is from the image processing tab up here at the top. And what you'll do is you'll come over here and you'll set the number of points horizontally. And by default, it's 20. I bumped it up to 30 just because I wanted to get a better result. At least I thought it would give me a better result. It automatically, you hit the generate button and it automatically generates the field there. And then what I did beyond that is I went through and I unselected everywhere that there was nebulosity. And then I added more down here along this bottom because I knew that that's where that amp glow data was coming. Then I checked, there's a box up here for dithering. I checked that. And then once I hit the apply, this is the resulting image in an auto stretch. You close out that, and then we'll go through to the next part. And there's, it's a color calibration. So the first part of it, you go through and you select an area of neutral background sky, and you apply that. And that basically is setting your black point. And then you choose a very bright section or a section with a lot of the color, and that's setting your, if you choose the brightest thing, you're going to set the white point. If you choose more of it, I think you end up setting more of a midpoint with that selection. I've seen it described both ways, but I used it as if I were setting a white point. And then you hit apply, and now you can see in here there's a lot more nebulosity down here in the bottom of this image. Okay, and then the next thing I'm gonna do is go back up there.
Okay,
and sel-
Trevor, hold on, back up. So what was the last operation you did to get that?
This was the color calibration.
Color calibration does that. Wow, okay.
And then the next operation is I'm doing a photometric color calibration where it goes out to a database and pulls what the colors are supposed to be from the database. And you have to know your focal length of your camera, and you have to know your pixel size of your camera. And then once you select those options, you apply that. It sets the color. And it'll come back and tell you that it's applied it correctly, or it'll tell you if you didn't set those settings right, it won't do it. And you have to be connected to the internet with the application for this to work, because it does go check a database. After that, I switch back to the linear view down there at the bottom like I was showing before. And you can see nothing looks like it's been changed. However, it has. Next, we go through and I'm going to do an arc sign transformation on this. And this is just to where I can just get the beginning of the nebulosity to where I could see maybe just a faint bit of the horse head over kind of where the pointer is. And then, of course, I apply that. Then next, I'll actually do a histogram transformation and try and get the histogram stretch where it needs to be. And so, by adjusting both the, you move the midpoint and the black point a little bit. And what you're trying to do down here is to make sure that you're not doing any clipping with the data, because it'll start showing clipping if you go too far with it. So I pushed it as far as I thought I could without clipping. And then when you're done with serial, you go ahead and you can save this off as a FITS file or a TIFF file. And then after I did that, I said, well, that looks good, but I'm going to take it over into Photoshop and do some more edits in Photoshop. And that's what I ended up with.
Okay, so can you tell us, how does this compare versus other ones you've used like Deep Sky Stacker, how, like especially the stacking and calibration?
As far as that goes, it's one was that before I was doing all of my stacking in Deep Sky Stacker. So that I was doing on a laptop. Then I had to take the files and transfer it back to my Mac to do the Photoshop because I didn't have it. Now I can do it all on one system. So I'm not having to bounce back and forth. And I find it a lot easier, because I got a pretty decent image and then, did some final tweaks over in Adobe. And this is what you can get with it. And I can tell you, I processed this image start to finish in probably about an hour and a half.
Well, did you notice any performance improvements like flat fielding or noise performance or anything like that?
No, I didn't. I didn't pay that much attention to it, Doug, to tell you the truth. But I remember early processing, there were, when I was trying to apply the flats and everything, I still saw some dust spots, but I don't see those in this. So I think it did a much better job at flat filling.
Oh,
Okay. So you have the Orion Nebula up here. Come on, where's the mouse? It's not moving.
Yeah, just to point out the horse head
Okay, so
for the
you
audience.
have, the horse head's gonna be, man, this mouse is not cooperating. Okay, well. Yeah. Yeah, that's it, where Doug was pointing. For those of y'all on the, out on the internet, you can say, I don't know, I'm having trouble with the mouse. It's not cooperating. So it's on the, if you're looking at it, lower left, and it kind of looks like a horse head, and that's dust in front of that ionized hydrogen. 250 millimeter. Yeah, with a 51 millimeter objective lens. So, yeah, red cat.
So I have a question. I've never processed anything. If you just put some stuff into this, does it tell you what to do, or do you have to already have an idea of what to do?
You kind of have to know what you're doing a little bit. But
is there one that you could just put something in and it's like, well, this is step by step what you got to do, or you just forever mess with it until you learn it?
Yeah, you're going to have to learn it. Basically, the main thing is you're going to have your light frames, which are the object itself. You're going to have your calibration frames, which are dark frames, your flat frames, and your bias frames. And those, through mathematical processes, reduce the noise, flatten the field, pull out any errors, remove hot pixels, that sort of stuff. There's a whole lot of learning to get to that point.
I'm going to help him with this question.
Okay.
How did you figure out how to use this? You see, was there a tutorial?
Yeah, and that's what I'm going to get to right now.
So there was a tutorial you found?
Yeah, I found one on YouTube.
That's to answer your question, Aaron.
This is how I learned this particular piece of software. There was a lot more to it in that software, where they go in and do some of the star reduction stuff like Doug showed in his images earlier. I didn't do that, but it is described in this YouTube channel. No, this one is open source.
Yes, and according to my phone, it has a tutorial built in.
Okay.
So Charlie, you should get a copy of Serial and go at it.
Just Googled it.
You go back to the black and white before your last color picture. Is there a lot more stars in that color picture than the black and white one? It looks like you suddenly got like twice as many little stars.
I think it's just because of the small screen that you're seeing in this.
Go back to the final pictures. That's what I'm looking at. That one and the one after that, the color one looks like there's like twice as many stars.
I'm not sure. Oh, yeah, they're probably washed out. Yeah, so, I did some dehazing and stuff in Photoshop and a couple other things that probably made them pop. Yeah, that's the big difference. This is just the final through the stacking process and the initial stretch. This is the final processed image.
Okay, next up, David with Star Party News.
All right, Star Party report for February. February 4th, we had outreach of the Hack Winery. A few more dates coming up, but I'll come back to this February 4th date. I put Clear Falls High School, oops, forgot the L. Postponed due to weather. I'm assuming they're working with you, Doug, about a future date? Okay. March 4th on Saturday, we've got Magnolia Creek Golf Course outreach event. I think some of you have been there for that. Appreciate you coming out in the past and look forward to it in the future. They do feed us a little bit, but you might want to pre-feed yourself before you go. Doug will talk about a little bit later, March 16th to 19th, Thursday through Saturday, with the clubs gathering at Fort McCavitt. 19th through 22nd is at the X-Bar Ranch. And we slide into April, April 1st to Saturday, we've got an event at Hack again. Then boom, end of the month, Hack again. May 14th to the 20th, for those that are interested, Texas Star Party. And right now, all we've got in the books are a couple of Hack Winery events that are tentative at this point. February 4th, thanks to Bob and Leslie Eaton, Chris Randall, Reed Klotzer, and Connie, we had I think that's wrong. We had four scopes, one binoculars, and roughly 65 in attendance. It was a little on the lighter side. I've been discussing with the winery. Chris here's getting all set up. Connie snapped a few pictures of the winery itself. It's really a nice place to have it if you haven't been there before. Pulling stuff out, getting set up. Shameless picture of me and Connie. Nice sunset that was there. Reed's got also getting himself set up here. We got the moon. The moon was a reasonably good target for the first part until the skies got dark. Then we started going all over the place. We went to Orion Nebula, Mars, Jupiter. Chris grabbed a few of the comet that was out there. So that's pretty much it for Hack. I do throw this up just as a little memorial that January was not, since we're transitioning from January to February, January was not exactly the best of months for manned space flight. But to never end on a down moment, I admit this discovery does seem to support the asteroid theory. So that's all, folks.
Hey, thank you, David, for continuing to be our Star Party chairman.
Hey, Doug.
What?
Real quick. Question came in. Anybody planning to go to TSP this year from the club?
Who? Ron?
Yeah, a couple? Okay.
And yes, that's the answer. There are a few. Hey, David just mentioned our trip to Fort McCavitt and X-Bar Ranch, which is next month coming up. So it'll be the 16th through the 18th at Fort McCavitt, which is free. You can just go out there and set up your telescope and have fun. It's a lot of fun, Thursday through Saturday night. Now what we're going to do is, then after that, if you want to, then we're going to go to the X-Bar Ranch from the 19th to the 22nd. And X-Bar Ranch is very different. Fort McCavitt's all free. You just go out there. So you can stay in a building or you can tent camp. X-Bar, you need to actually rent one of the cabins and make a reservation in advance. You go to their webpage and they have cabins. They have a use of a lodge in the kitchen. They have power out on the observing field. It's really nice. Bortle 2 skies both at Fort McCavitt and X-Bar. Fort McCavitt actually is just slightly darker than X-Bar, but they're both Bortle 2. Right now we got 6 people. They're going to X-Bar, and last time I looked, there's one cabin left that's near the observing field. This is the observing field behind here, and then this is the back porch of the lodge. But there's also some cabins right by this. There's one cabin left that's near the observing field, and there's one cabin that's just right across the parking lot that's still available at X-Bar if someone wants to go to this. This is kind of what it looks like. It's a really beautiful ranch. There's these hiking trails down here you can go on. We have meals up here. You go in here. This is a kitchen area where they have tables and a kitchen that you can do stuff out. Beautiful porch out here in the back and rocking chairs. Really peaceful, nice place to go, and it's just a lot of fun. That's what? Talk to you till you talk into a microphone.
What town is that near?
Here, El Dorado, Texas. El Dorado. You know where Sonora is, probably. Yeah, it's maybe 12 miles west of Sonora. It is Sonora, right? Brandon, is that little town we go to? Sonora, yeah. Okay, Brandon, we go down there and eat at Pizza Hut. So anyway, okay, so Sonora, you go 12 miles, I think, west, and then you go about 7 miles north. It's between there and El Dorado, Texas. But the family that owns this place, they couldn't be nicer. I mean, it's the Metter family. They're just great. I mean, you got to pay to go there, but it's sure a lot more comfortable than, sleeping in a tent like which is what I normally do. But it's got this nice kitchen area here, everything you need, stove, refrigerator, the whole bit. And here's some more pictures. This is right across from the kitchen area. There's these tables sitting out here. There's a meeting area back there. There's actually a TV and a living area right here. If it's dark skies, we can sit in there and watch movies or whatever. This is kind of what the cabins look like inside and outside. There's a swimming pool there, Ron. You could go swimming. I wouldn't go in that swimming pool for anything. It doesn't look like that in real life, sorry. Okay. All right, so that's fun. If you guys want to go, it'd be nice. Let me know if you're going so we know who all is going to show up at this thing. Okay, door prize. Prize ticket. I got 752. Over here, you. So I have either a moon map or a Starliner mouse pad. You like the Starliner mouse pad? Okay, fine. Didn't have to tell you the other ones, huh? Okay, very good. All right, good. All right, here's another one. That one is torn off. I can't see it. Oh, 7746. 76. Righty, 749. I'm going to 749. Okay. Almost the same, aren't they? Seven, 3, 7.
Yay!
All right, come on. Okay, so I have a moon map. I have the Kepler spacecraft's metal model of that. I have some cool decals. One of them says, let's see, it says, "I'm an astronomer. What is your superpower?" You put that on your car? You like that?
Let's go with the moon map.
You want the moon map?
Yeah.
Okay, I see you love that decal, didn't you? Okay, one more.
I already have my NASA's sticker on.
Oh, that's even more beautiful. Okay, so 713. All right, come on. You want a moon map? Okay, hold on. Let me tell you again. I got a moon map. I got a Starliner mouse pad. I got I'm an astronomer. What's your superpower? I've got the Kepler telescope. Yeah, you didn't know it was so small, did you? You can't have all of it. I have a book says planets, which I don't know what that's about.
Probably planets.
Which one you want?
I'll do the movie.
Okay, excellent.
Thank you.
Okay, very good. Okay, next month we will be here with Justin's going to tell us about Python for the universe. That's going to be cool for anybody that's interested in programming, especially. Here at the LPI, and then April 14th, I know a lot of people have been asking me when we're going to be back at UH Clear Lake. Okay, April 14th, we're going to be back at UH Clear Lake. We're going to have one especially for the physics department called Light Waves and Their Uses, which will be a lot of fun. hopefully we can get all the physics students to come out for that one. I see you guys shaking your heads, right? Yeah, physics students. All right, good, good, good. Okay, so that's it. See you at Mod Pizza directly after the meeting. Thank